Well, good evening, everybody. I'm Grant Christie, as you probably know, and I'm going to just sort of take us through a bit of a journey that we've been on at Stardome for the last sort of nearly 20 years now. The work we've done at Stardome, I've done with Tim Natush, who I've added his name here. He probably didn't want it, but it's there because we've been a team ever since we started. It's Tim's made a great contribution to the operation. So the dome that we use for research is this one that's painted white, and it was installed in 1997 when the building got rebuilt. It was originally built by the Wooden Boat Company in Auckland, so it's a very well-made dome. It's worked very well in practice. It's got two shutters, a top one that slides back and a bottom one that tilts down when we need to, but we generally don't often have to tilt it down. And there's a solar panel on the outside that charges the battery that runs the motors that open and shut the dome. So basically this telescope is now operated only remotely, and I just do it from home. And so it's very convenient, only takes a few minutes to get it up and running. So the rotation of the dome is done by what's effectively an electric gate opener that you'd use for a driveway gate. That's worked very well. The dome rotates full 360-degree rotation in 60 seconds, so it never holds us up. So the telescope we're using is a Meade 40 centimetre F10 ACF, Advanced Coma Free they call it, which is a sort of a Clayton's Ritchie Cratian, but it's optically very good on when it's properly collimated. When on a good night in Auckland, we get images that have that are sort of down around the low 1 arc-second range. And often, most of the time, they're around 2 or 2 arc-seconds. So it's nice, sharp images for the most part. The field of view on the left-hand side shows our camera field silhouetted against the moon. We don't point it at the moon, but just give you some idea of our scale, 17 by 10 arc minutes. And the mount we've got, it's not the original one we started with, but this is a bisque mount, Paramount ME2, that we bought in 2015, I think it was, that we obtained it. And it's been phenomenal. It replaced an earlier Paramount that's Steve Henley's rebuilt and repurposed out at Kumu, so it's still working happily. This mount carries quite a bit more weight than the original GT1100S, but this is all the bisque mounts are really top quality stuff, and it's capable of pointing to very high accuracy all around the sky, and tracks very well most of the time. And it's controlled by bisque software, the Sky X. Our camera is a SBIG STL6303, and we got this. This was provided by Microfund, Ohio State University, to us in about 2007, if I remember correctly. So it's got a guide. Well, the down here on the bottom left shows you basically a cartoon of the size of the sensor. There's a guide chip there, which is a very small chip, but it's suitable for guiding. The camera has worked extremely well. It's actually got embedded in it a 5-position filter wheel, which holds 5 2-inch filters, and currently it's populated with 4 of those. The cartoon on the right-hand side is its big brother, the ST11000M, and that's the camera that we have bought but haven't really used yet for the Zeiss And you'll notice that the camera we're using is SB2, so a full frame download takes around about 30 seconds, 1x1 bin full frame, which is a bit of, well, we're kind of used to the 30-second delay, but its big brother is got USB 3 and it downloads in a couple of seconds a much bigger image. So that camera is just waiting to be used on the Zeiss. The other really great bit of kit that we've got is the Optec TCF-S temperature compensating focuser. It's a 2-inch focuser. It's got a range of 15 millimeters and 10,000 steps. You can see in the photo there's a temperature sensor that plugs into the camera. The sensor gets stuck with an adhesive tape onto the body of the telescope. And our telescope's an alloy, not carbon fiber, so it does expand and contract with temperature. But we've got this very well calibrated now, so effectively the focus never changes, no matter what the temperature is doing. So long as this instrument is working, and it's worked very well for us so far, then we really don't have focus shifts with temperature. So I could really recommend them as a tool. We've also got we've got 2 filter wheels. There's a front one, which is it holds 5 filters. Currently it's populated with a BV, R and I, which are basically the Bessel filters, and one is blank. When you've got multiple filter wheels, you have to have a blank in each one so that you can select all the filters, and that's fairly obvious, I guess. And the back one, which is actually in the camera itself, has the Sloan filters that are just G prime, R prime, I prime, which are the sort of gradually, steadily replacing the older BVRI. Currently, we have use for both filter sets. Some people want I photometry to match other telescopes that are contributing to an event, something we're doing. And the R filter gets used a bit too. So the I and the R on the Bessel set do get used occasionally for the microlensing. Currently, our microlensing with microfun doesn't use the Sloan filters. They're pretty expensive, and most people don't have them, so that's probably a good thing. We've got a spare space in the back filter wheel that we could put another filter in, but we've got no particular need to. So we're pretty regularly using the GRI, the Sloan filter set. Subo Dong in Peking University is following up objects that Sloan, the Gaia satellite is finding. And everyone doing those follow-ups of those objects is basically using the GRI Sloan filter set. So it's good that we've got it. We do have a spare set of that for the Zeiss as well, but they could be reused out at Kumu if the Zeiss isn't using them. These are the transmission curves of the BVRI filters. They say they're legacy filters because they're sort of basically on the way out now. The manufacture of these filters was never quite standardized the way the newer filters are, so each filter set was a bit different, and you had to be pretty careful about getting them properly calibrated against well-measured standard stars to be able to sort of match them to other people's photometry. But they still have the uses, and we do use them as well for other projects. The Sloan filters, you can see the difference between the old style, which were just basically sort of the manufacturing was fairly basic when those were designed, today compared with the Sloan filters, where the 100% transmission, very square cutoff, not much overlap, and everybody's filter sets are essentially the same. So there isn't quite the same need to calibrate these filters before working collaboratively with other people, because basically to a fair degree everybody's got the same transmission wavelengths. This picture shows the telescope inside the dome, so it shows the dome interior. It's a very cozy dome, I might say. It's very watertight, and so that stainless steel shutter there, you can see, gets dragged back by the motor over on the right-hand side there. You can see that's the garden or the driveway gate opener, repurposed, and that was designed by a local engineer, that whole setup there, and it's worked extremely well. And in particular, its main thing is that when it's pulling the shutter back, it's pulling evenly on both sides because of this connecting bar. So there's sort of basically sprockets on each side, so it gives a pretty even pull. There's some things we could do to sort of make the sort of less drag. That would be good, but it sort of works okay at the present time. And say opens in about, the top shutter will open in about 20 seconds, 30 seconds at the most. And you can see there on the left side that there's a bottom shutter there too, which once the top shutter's open, the bottom one can be lowered down, and it's a radial arm actuator that lowers the bottom shutter down. So when the bottom shutter's down, we can literally point to the horizon. And although there's trees around the observatory in One Tree Hill Domain where we are, there are sort of quite significant gaps in the horizon where we can literally point to the horizon. So, and sometimes we've taken photometry and done some astrometry on a comet on one occasion that was only 5 degrees above the horizon. So it's so unless we get unlucky and get whacked by a tree in the way, we're pretty good. But 90% of the time, we never need to put the bottom shutter down. And so this is the business end, showing the camera. This is the temperature compensating focuser with the temperature probe going, that white tube going there. It's up to where the tube is, where the sensor is stuck onto the alloy telescope tube. This is the front filter wheel, maybe optic, and it's a 5-position filter wheel. It's been very good in operation. Only recently, having used it for a long time, we had a O-ring, rubber O-ring failed, and but fortunately we were able to get one identical locally here for $5 from a place about 2 kilometres from the observatory. So that was no big drama, and so it's been very, very reliable. So the key software that we've got, the main one, because we've got a bisque mount, is it's pretty much you have to use the SkyX software. It's really designed to work with a Paramount mount, and on the whole, it works extremely well. The Paramount comes with an extra program called T-Point, which is used for basically refining the pointing of the telescope, and it builds what's called a pointing model. So once you've imaged, typically, I think the next slide might actually show it. There it is. So that's a cartoon showing our celestial sphere with about 400 points on it. And so when we do a mapping run, the telescope is programmed to automatically slew to each of those points on the diagram here. Take an image, astrometrically solve it, which tells it where it's pointing to within about a 1/10 of an arc second, and it then logs that point, so it knows exactly where the telescope's pointing, and it does that to, in this case, it's something like 400 odd points over the sky. And then it fits a computer model to that, the pointing discrepancies that it's detected, although they'd be small, it can map them out. And so basically you can get really good pointing and tracking using that method. So it's So we've got the sky, we've got T-point. We use to control the camera, we're using Maximum DL, and we've used that basically forever. And it's gone through many changes now. It used to be Maximum DL 5 or 4 when we started. It's now up to 6. We don't have the latest version because the upgrades cost quite a bit of money, and we don't have any problem with the one we're on. So we don't want to sort of test our luck by getting an update for hundreds of dollars. The Optic IFW is the filter selection software that comes with the filter wheel, and then there's a temperature compensating focuser. It's got a software that runs the focuser. Tim and I, or Tim actually introduced us to it, was the D4 time program, which enables we have that installed, and every 5 minutes that looks up a very accurate time source and resyncs the computer's time. So the computer's never off by more than couldn't be off by more than 1/10 of a second at any given time, and that just keeps doing that forever. Pinpoint is a program for doing astrometry. If you're doing comets or asteroids in particular, then Pinpoint is very good for that. We haven't done much astrometry in recent times. We've just had enough to do with photometry, but it's certainly a very good program. Jenny McCormick, who may be sitting in on this, uses it quite a bit. And Stardome is a program that keeps our dome synced with the telescope. So wherever the telescope moves to, the Stardome software drives the dome around to keep the two lined up. So that works very well. I think it was free and no complaints. And I think Tony Burns built the electronic card and stuff that interfaces for us. So I think I've probably said enough about the calibration of the pointing, but it does certainly improve. I don't see the point in not doing it if you've got a paramount, or in fact, even with the Zeiss telescope, it would the Zeiss is effectively now a large paramount, so it will definitely benefit from doing a detailed mapping run in due course. So once with a camera, when we're working, we take CCD frames, obviously, and in order to calibrate these frames, we don't actually work towards making a picture pretty. I mean, we all think our pictures are gorgeous, of course, but more important to us is that the images are sufficiently well calibrated that we can, as best we can, to give us the best possible photometric measures, where we're measuring the brightness of things off our images, and we're not taking pictures for public display. So to that end, you have a thing called the bias frame, which simply measures the amount of readout noise in the camera, and you have a dark frame, which accumulates, measures how much noise, gradually the dark noise accumulates as you take a long exposure. So you need to have a dark frame of the right exposure length to subtract off your science frames, and also flat frames. You can use, there's different ways to take flat fields. You can use a screen of some sort. People try all sorts of different things. Personally, we've always just used the twilight sky. The downside of the twilight sky is that you're having to, you have to have a twilight sky. So if it's cloudy, tough luck. If it's raining, tough luck. So you don't always get a twilight sky. And for our filters, given the 30-second download time of the full 1x1 bin frames, we are fairly tightly constrained in how many flats we can take on a twilight. But if we had the faster download USB 3 camera, then we'd be able to get twilights would be easier. But there's only about for our filters, so you basically need flat frames for each filter, for each binning that you're using. So that's, in our case, we've got sort of basically 7 filters that we have, and we operate in either 1x1 or 2x2 bins. So that's a lot of flats that you have to get. But fortunately, so long as we don't move the camera or do anything to it, take it off, as soon as you do anything like that, you need to redo your flats. So we try to go as long as we can without having to touch the camera or move it in any way. And of course, your science frames are made with the shutter open on a dark sky, and you get a nice picture of the stars. But in order to use those for science, you really got to apply the corrections of flatting, dark subtraction, and bias subtraction. It's pretty easy. I mean, Maxim DL does it automatically once you got it set up, so it's a bit of a no-brainer, really. The cameras are a photoelectric device, so our camera that we're using at the present time is this KAF 6303 sensor. Its quantum efficiency is around the 70%, 60-70% range, and the peak sensitivity is around 650 nanometers, so it's in the red, definitely fairly well into the red. And it doesn't have much sensitivity. It's okay in the blue, but it's fairly well down on the blue filter, so we don't take that many images with the blue filter anyway, so it's not a huge issue. Most of the microlensing stuff we do is somewhere around the peak sensitivity, and that so it's not really a huge problem for us. So basically what we do is, as I say, what we do is we do photometry. We measure the brightness of stars as best we can, and typically our photometry on brighter targets, anything brighter than about magnitude sort of 15, is typically 1% or better photometric accuracy. So so we do okay there, and if you need to do fainter things, you just image for longer and stack up more images to improve your signal to noise ratio. So we've done photometry down to nearly magnitude 20, either though we're in the middle of Auckland City. And we've had papers published that in fact use that photometry on a gamma ray burst on one occasion, where it got down to faded to 19th magnitude. We still got something useful. We can do astrometry, which is like measuring the positions of comets and asteroids, but generally we leave that to others. We've got sort of gear that sort of gives us sort of particular advantages in photometry. We've got good filter sets and everything else, good tracking. So we tend to stick to the photometry, and would only probably do astrometry if there was nothing else to do. But we can do it. And if someone was keen and wanted to do some astrometry with the telescope, we could probably arrange that. We like to start to do unexpected things. So we don't tend to do too much on stuff where like measuring things that are pretty predictable that other people can do. So we tend to work on more what we call transient objects, things that do things that are not likely to ever repeat. That's why microlensing is we're drawn to that for one of those reasons, that if you take the data while the event's going on, it'll never happen again. And we find that kind of exciting, and that's why we're drawn to that. But having said that, as I'll say later in this talk, that we have done some work on an eclipsing binary as well. The things we point at are notified by our collaborators. So our collaborators in either Beijing, Peking University, or Ohio State University, they're looking at the output from the survey telescopes. We don't concentrate on that. They're watching for things that look like they're going to be exciting, and they do the call to say that, hey, we want a particular star image and get photometry on it. So we do that, and we wait for those calls, and when we try to take them. And so it's basically the same as what happens with Jenny McCormick's telescope. She's very active and has been right for 20 years and this sort of stuff. And Steve and Co out at QMU are doing the same now and doing very well. When we start looking at an object, typically most of the time, the time scales we're dealing with is things can be changing on a minute-to-minute basis, and that could go on for a few months, but seldom longer than a few months. And most microlensing events have quite a limited duration, and they never ever repeat. So we have so once an event starts, then we keep taking data until it's decided that, usually the call's done by whoever we're collaborating with, that they decided that it's kind of over. Of course, kind of interestingly, QMU got a really good discovery of an Earth mass planet just when they were taking calibration frames after an event was over. And so I think our collaborators, professional collaborators, probably pulled the plug too early sometimes. And we've had sort of similar things with them as well. But generally, once a microlensing event's over, it's never going to repeat. You forget it and move on. So basically, we kind of got into gravitational microlensing kind of by accident. Phil Yock, who's a former professor of physics at Auckland University, Phil had been nagging me for years to, once we started doing CZD photometry, to look at microlensing objects. And we were sort of kind of new in it at that stage, and there weren't any it wasn't clear collaborations. Amateurs had never done anything like that before. So in 2003, I did start looking at some of the MOA ones that were being Ian Bond in particular, who was running the MOA telescope, which was only a 24-inch, a 40-centimetre telescope in those days. They weren't using the big one they've got now. So their telescope wasn't that much bigger than what we had. So I did some of that stuff in 2003, but it never got used. I sent it off to Ian, but he was, I don't think he ever received it in Paris, where he was on sabbatical or something. So nothing much happened until the following year, when Jenny McCormick was looking for something to do and saw a request from a guy called Andy, and wanting observations of something. So Jenny was at a bit of a loose end that night, so started observing this event that he wanted. And then anyway, to just cut a long story short, it turned out Andy was a senior professor at Ohio State University and one of the sort of world gurus on microlensing, and this was a microlensing target, and Andy was desperate to get people to look, and he was wanting people with 1 meter telescopes to do this. Jenny's telescope was a 0.1 meter telescope. Once he grabbed that, he still was, he's a very interesting guy, and didn't want to upset Jenny or anything like that, so they were happy to take her data, and she sent it off, and they were able to process it through their pipeline, photometric pipeline, and Ohio State University. Jenny mentioned it to me, and I recognized that this was a microlensing thing. So the next night we did it as well from Stardome with in that stage, the Celestron telescope. So we started working together on these sort of objects. It was a learning experience, but that's basically how we got into it by accident. But it was been a very useful thing. Suddenly, the staff and faculty at Ohio State realised that, hey, because one of their problems was that they didn't have many small telescopes or telescopes that are available at short notice. They often, to them, a small telescope was 1 meter. But getting barging in on special time on somebody else's 1 meter telescope was pretty hard to do. You sort of upset a lot of people who had the time booked. But once they realised that actually amateur-sized telescopes could do the job, they it kind of changed their whole way of thinking and realised that there were a heck of a lot of smaller telescopes around that could do microlensing. So it grew from that. So it's now sort of a regular, normal thing to be doing. So that's a bit of the backstory, but the surveys that are now running is OGLE, Optical Gravitational Lensing Experiment. That's run from a Polish collaboration in Chile. They got a 1.2 meter telescope. It doesn't sound very big, but it's have exceptionally good seeing at Cerro, some of the best in the world, often below an arc second, half an arc second even. So they have particular advantages due to their sight as well, even though the telescope's not large. Then you've got the 1.8 meter at Mount John, which has been working extremely well now since about 2010, I think, and it's it's working extremely well. Mount John doesn't have such good seeing as you get in Cerro. It's got it's probably a lot of the time it's about the same as ours in Auckland, and then there's a new network which is relatively new. It's been operating since about 2016, I think. The Korean Multi-Telescope Network, KMT. They've got 3 1.6 meter telescopes based around the southern hemisphere. So one in Chile, Siding Springs in Australia, and Sutherland in South Africa. And their strategy is that these telescopes work in a coordinated way, so that they are taking data 24 hours as the night moves around the southern hemisphere. Each telescope, it's like a tag team takes over from the other one, and they keep doing that. So they get very uniform data from their telescopes. They're very efficient. They've got huge sensors on there, so their field of views are enormous, about 4 degrees square, I think they get. So they certainly hoover up a lot of data. So we've got these 3 different major collaborations working in the southern hemisphere, discovering microlensing events, and then we get notified of ones that are particularly interesting, and that's when smaller telescopes like ours get in on the game. So microlensing sounds sort of scary, but it's actually something that's predicted by Einstein's general theory of relativity. Basically it comes from the idea, I think most people understand nowadays, that something like the size of a star distorts the shape of space. The sun does that. So even a small star like the sun makes a significant distortion to the local space around it just because of its gravity. And so this means that the path of light takes as it goes past that mass gets changed, and so effectively a big mass sitting there in space can act like a lens. And the mass itself could be a star, it could be a white dwarf, a degenerate thing like a dwarf, or an even more degenerate thing like a neutron star or a black hole. So basically we don't care. The thing that's doing the mass that's there doing the lensing doesn't have to have any light at all coming from it. The light is coming from the source star beyond it that goes past that mass and comes to our telescope. So on the way past that mass, the star's position gets distorted by the warp gravity in that vicinity, and that's kind of what we're measuring. And from that we can work out the mass. Not we, but our collaborators can use our data to work out the mass of the objects. So this is the only method you could use to find a black hole in the middle of the galaxy somewhere, or anywhere in the galaxy. But and we've some of our events have also discovered black holes and neutron stars that way. Right. So the first time we really had a good event. This is basically with Journey at Farm Cove and Stardome at Auckland, I'm saying we, was in 2005, Anzac weekend, and we started observing an event that got brighter and brighter. You can see the light curve there. Don't worry too much about the cartoony bits. And you can see it has a remarkable light curve. It came up from fairly faint down around magnitude 19, so it would be too faint for us. But by the time it got up to around about magnitude 16, it was certainly within range of our telescopes. And that's where the action happens. It's those pointy bits on top that are really important. And so we, Jenny at her observatory and me at the Stardome, we ran the telescope and we took data, and our data is used there. You can see UFun Farm Cove and UFun Auckland are our two, and this turned out to be there's people who specialise in trying to then fit a model to observational data. So that's quite a process in its own right. I don't know too much about the details of how they do it. It's a bit of a it can be quite tricky, but in this case these spikes were so obvious and everything, they came up with a model pretty damn quickly, and it showed that the star that was doing the lensing was a red dwarf, about half the mass of the sun, and those two spiky bits there were caused by it having a massive planetary companion, and that planetary companion was 4.4 Jupiter masses. Now, this was a complete surprise to astronomers, because the assumption had always been that if red dwarfs, which are very, half the mass of the sun, would only have little planets if they had any at all. So here, the very first time we got to, with microlensing, got a look at a red dwarf with planets, it was 4.5 times the mass of Jupiter. So that suddenly the whole idea of the way planets formed got revised after this paper was published. And it was quite an exciting event to be on. Jenny will remember it well, I know. And it was Anzac Day weekend 2005. And that was actually the first time a planet had been discovered or not the first one actually, but the first emphatic one that was clear, absolute, no question, no argument about it. So Phil Yock, who's on the right here in this picture, unfortunately I caught him having a nana nap, but Phil was always the one who was the great advocate for doing microlensing. He's been advocating it for a long time. He had been nagging me about doing it. And Ian Bond there was a PhD graduate of Phil's. So he was obviously well versed in microlensing, and Ian now runs the whole operation at Mount John. He's the principal scientist there. And of course, Jenny as well has no more background than I do in general relativity. So, but it was really nice to be mixing into these folks and have continued to do so ever since. And this got a lot of attraction in the press, particularly as that a massive planet had been discovered around a little star, but also the fact that amateurs have played a significant role in getting it. That seemed to be the sort of sub-story. So that's an Emerson cartoon, which was almost right. It wasn't at the edge of the solar system, but it was certainly around about 15,000 light years away. And that's actually the field. Oh, sorry, that's not, no, so this is a different event. I've moved on. So this is another event that did with the folks in Ohio, also in 2005. This is a star in the small Magellanic clouds that had been detected because these survey teams were not only looking at the Milky Way and the bulge of the Milky Way for microlensing events, they were also looking for them against the backdrop of the Magellanic clouds. And in fact, in early 1990s, when they first started doing microlensing, they were only looking at the Magellanic clouds, hoping to detect stuff in the halo of the Milky Way galaxy. So anyway, so we did this event, and and it turned out to be a star in the small Magellanic Clouds that was being lensed by a black hole in the halo of the galaxy. So that was basically what that original survey had been trying to find, never did, and this one here, which we participated in, did. And so this was basically the story of that. So in the diagram up on the top left, you have telescopes on Earth and also the Spitzer Space Telescope. So they managed to drag the Spitzer Space Telescope into this. So our telescope on Earth was looking at this event in the Magellanic Cloud, in the small Magellanic Cloud. And for some of that time, Spitzer was also looking at it. And the big advantage of that is that Spitzer was a long way from Earth and the other side of the sun, basically. And so it was well separated. So it was a big parallax. And what that did is it constrained the distance of this black hole. You can see the sort of little cartoon of the black hole going across between our telescopes and the small Magellanic Cloud. And it told us that told the experts, I don't include myself in that category, but it constrained where the lensing object was, and it was clearly not in our neighbourhood in the Milky Way, in one of our spiral arms. It was actually somewhere in between the Milky Way and the small Magellanic Cloud. So it was a free-floating black hole traveling through space, and there's nothing else, no other way that could be discovered other than by microlensing. So it was a wonderful example of that. And the diagram over on the right, basically it shows that the graph at the bottom shows you the difference in the photometry from what the Ogle telescope recorded and what the Spitzer telescope separated on the other side, well away, several AU away from Earth, managed to get. And from that difference of those measurements, that gave them a measurement of the parallax and nailed down constrained the distance that this black hole was. And the fact that it produced no light led them to believe it was probably a black hole. So that was kind of exciting. So so currently the surveys that are running Ogle, MOA and KMT are detecting upwards now of 4,000 microlensing events a year. So when we started in the early 2000s, it was more like 2,000, more like sort of less than 1,000 events a year. So now these survey telescopes are hoovering them up very efficiently. In many cases, they're finding the same one, so they're not all unique. But that's a huge number of these events. That interestingly, that when Einstein first realised that publish a paper in 1935 that sort of laid down basically the mathematics of gravitational microlensing, he knew that the chance of seeing two stars lined up to the precision required was so remote that he predicted that it would never be seen. And now we're seeing with computer-controlled telescopes and so on, we're finding 4,000 of them a year. He'd be surprised and pleased, I'm sure. So most of the events that happen are just one star lensing a more distant star, it provides some good statistics for people interested in populations of stars and so on, but they're not really of interest to us. We're interested in ones where the lensing star or object is something unusual. It's either a planetary system, could be a double star, though they're not quite so interesting, but they do, they do produce spectacular light curves. But primarily, most of the work is focused on looking at a star that's got planets going around it. That's basically what they're looking for. So anyway, so the nearest star, it's I've mentioned before anyway, it's a general relativistic effect. The lensing star may be a binary, may have have planets, which make more complicated, more interesting lenses. Currently, there's no single telescope that can actually resolve. So if you've discovered a star with planets going around it, there's no telescope that can currently resolve them, because the lensing star is too far away by far, and you just can't do it. But so you can infer that there's these planets there just from the mathematics and general relativity. But one project I took data for, which was quite exciting, was a microlensing event that occurred not in the galactic bulge in a very dense stellar field. It was just out in the sort of spiral arms. It was a fairly low density field, so it was pretty improbable that you'd get microlensing there, but it happens. But so data was taken on that, and Subo Dong in Peking, who was working with on this, he rapidly applied for time at Paranal in Chile to get the 8.2 meter telescopes to work as an interferometer. Now that was the original design concept with those 4 great big telescopes at Paranal. Have been working independently as fantastic telescopes, but it's only in recent times that they've actually got the interferometric part of them. They're always intended to work as a 4-telescope interferometer 120 meters across. And that gives you the resolving power of an enormous telescope, much bigger than anything else that was available. So Subo rapidly put in an application to time, because they'd only just for the first time been using the 4 simultaneous. He knew that. The director granted them the time, and they did, in fact, were able to work interferometrically on this target that we would have been looking at, and it obtained ultra high resolution images and was the first ever actual resolution of a gravitational lens. So it was phenomenal. The 4 telescopes were only working for 15 seconds while that observation was obtained, and then they lost the sync on it, but they obtained the observation. So that was pretty stunning. So that's something for the future. That's going to become more and more common, that they'll be able to actually image these and actually see the fine details of the lenses. Probably one of the most exciting ones that we were involved with was the discovery of a Jupiter-Saturn analog, and this was in 2008, and it was so this was a star that had 2 planets going around it, and it turned out the star was a half a solar mass. I think there's a diagram of it. Yeah, I'll just run forward. So basically the top cartoon shows our solar system with a 1 solar mass star, our sun. Jupiter and Saturn are by far the dominant objects, and there's other detritus there like the Earth and Venus and other things. The system that we got the microlensing of was a red dwarf, half the mass of the sun, and it had a Jupiter and a Saturn, the same mass ratio so in other words, a 50% scale model of our solar system. Now, we don't know, because microlensing is not sensitive to planets close to the star that's being lensed, so we don't know if there are inner planets at all, and it's not very sensitive to outer planets either. So basically, these planets in this system were right on the sweet spot for microlensing, and they were clearly detected. And to this date, as far as I'm aware, this is still by far the closest match to our solar system, except that it's a half-scale model. It's not the Dinkin McCoy yet, but that was a very important paper, and it ended up in Science as well. This is a picture of the 4 8.2 meter telescopes at Paranal, and so these can be combined and operated as an interferometer. And underneath this tunnels under here, there's some auxiliary extra telescopes that also contribute, and they do all the magic with interferometry, not my field. and put this all together. So this is going to be something to watch in the future. They're going to get fantastic resolution. That's what this instrument was built for. And probably in the next few years, it'll become sort of more routine. Now, just let's see how I'm going for time. Okay, so the last little bit I'll talk about is a project that Tim and I have been doing on this Westerland 2 star cluster. This came because there was a paper presented at an IAU conference held in Auckland in 2016. And the presenter from Belgium was talking about this cluster and thought, well, that's interesting. That's well placed for us. So we started observing it and taking data. So that image there was taken with the Hubble Space Telescope. That's not my image. Otherwise, I might win the Harry Williams Trophy. But you'll see my image in a little bit. But this is an image taken. So basically, this is an extremely important cluster in Karina. Very dense. It's one of the youngest and has some of the most massive stars in the galaxy in it. And in particular, this one here, WR20A, it's a binary star with very high mass. It's 83 and 82 solar masses each. So it's one of the most massive binaries that is known. This seems to be its birth cluster over here, though at the moment theorists can't explain what it's doing out here, because this is so heavy that if there was it was ejected from the cluster, how do you eject 160 solar masses out of the cluster? So that's an unsolved issue at the moment. But anyway, there was a lot of interest in this binary star here because it's actually a Wolf-Rayet star. So it's extremely luminous, 1 million times the luminosity of the sun, and it's got a lot of similar stars buried in this cluster as well. So it's a very interesting area, and that's a Chandra X-ray image. This is our image. So there's the cluster there. That's WR20A there. We have something like 10,000 images now of this taken in a whole lot of different filters. It's I'll show you a plot of it soon, but we can also actually now resolve right into the center of this cluster. So we've got software that means we can do professional grade photometry right of all the stars in this cluster, and we've got a huge amount. Now, you'd think that professionals have been looking at this cluster for years, but in fact they haven't. They threw the Chandra, the Spitzer, and all these other Hubble and all those added in a big sort of intensive effort some years ago, but apart from that, nobody much looks at it. So we've got a long baseline of photometry on this cluster, which is extremely interesting. And there's so it's 3.7 day period, and this pair of massive stars in this eclipsing binary are well, it's really, I think JELDRIDGE at University of Auckland, she'll be, knows well about this and is a specialist in the evolution of really massive stars. So there's a lot of interest here locally in this object. There's a whole lot of other. That's just a 3D plot of that central cluster. So we can actually resolve. We've got software now that can resolve all the stars there, and it's a work in progress. So this is a typical light curve. Tony Cooper's been doing great stuff too, helping us. He's doing work out at QMU as well, doing great stuff there, but he also has been a help here on this one. So these are many nights of data that's been superimposed to produce this light curve. With such massive stars, they're likely to be unstable, so it's not entirely surprising that when we're seeing them side on, which is when they're up in this part, I'm not sure if you can see my pointer, but at the top of those two parts of the light curve, you can see it's fairly non-repeating, and that's when you're looking side on at the two stars. When they're in eclipse, you're looking at basically only one star in each, either one or the other. but when we're looking at them side on, we're actually looking at the space between the stars, and we think there's a lot of collisions of very intense stellar winds are colliding, producing this irregularity. But we've got a lot more data to add to this. This plot was done about 3 years ago, so we've got more to update this. So thank you very much for your attention, and happy to answer any questions if there are any.
Thanks for that, Grant. That was really, really interesting. Certainly for me with the work that we do out at Kumu. We just got one question in the chat. I think it's a clarification more than anything from Jenny McCormick. There is time for other questions if anybody wants to get in there quick. Jenny says, hey Grant, you stated the Spitzer telescope was several AU away, or did you mean the foreground star was several AU away? Can you explain that again regarding the black hole in the SMC? And she mentions that the orbital height of Spitzer is only 568 kilometers.
Spitzer was in a wide orbit, and I think they moved its orbit late in its life, because that's away from the Earth, because that was contaminating. I'm pretty certain it's I'm right on that. So it was Spitzer that was moved away. I mean, they all started off orbiting the Earth originally, but yeah, I'm pretty certain of that. I'll double check, but I'm pretty certain that's right.
There's no other questions on here, but there is one sort of point that I noted during your talk, which me as an IT geek and somebody who's faced the same problem at Kumu has had, and that's the time synchronization. A question I get a lot is, well, Windows can synchronize the time anyway, why do you need to bother? And that's
yeah, well, that's right. Windows has come on in the years. We just haven't turned that other thing off. We possibly don't need it, but it has been faithfully logging every. We've got a log file of where it writes, and every now and again we have to clean it out. But no, it might not be necessary.
Well,
but,
as an IT geek, it's still necessary. So just let everybody know.
Okay.
So Windows time synchronization is certainly not accurate enough, so you do need some additional software to do that. We have had another question, so I bought us a bit of time to get another question, and that is, you mentioned a black hole between the LMC and the Milky Way. Do we have any idea how common these rogue black holes are?
It's a good question. Somebody, I haven't seen any detailed analysis, but somebody would have used that one case to put a limit on how many there must be floating around. But I mean, it's been realized for a long time that every time you have a supermassive binary star, a bit like WR20A, when one of the stars ends up exploding as a supernova, it can eject the other one. So there's plenty of mechanisms by which stars can be ejected. Probably not supermassive ones, just because that needs a lot of more energy. But yeah, so there's plenty of stars that have probably been ejected from binary systems. Two binary systems interacting with each other can accelerate, knock stars off. You get that in globular clusters a lot. So there's a lot of stars get ejected from, ultimately from globular clusters, which are orbiting outside the Milky Way's disk. And so, yeah, so globular clusters are very dense. So you get a lot of close interactions. There's a wonderful paper, if you look it up, I think it was in the Astrophysical Journal, maybe the Astronomical Journal, on the promiscuous lives of globular clusters. And they did a lot of computer simulations that showed that globular clusters that have a lot of binaries in them, they are often exchanging partners. So these binaries are interacting with each other. Sometimes two doubles will come into close proximity. One of the doubles will grab one of the stars from the other one, and the other one of the double will get ejected out of entirely out of the globular cluster and end up just drifting in the halo. So there's plenty of ways in which the halo can get populated with stars. There's obviously not a lot of them, but the fact that we sort of having to get microlens by 1 was pretty good. But I'm sure the theorists you probably used that example of 1 to put a limit on, or some constraint on the number that must be out there. But time will tell. I mean, I think some of these microlensing surveys will start. We need more microlensing events of that type to constrain it more.
Thank you very much. Well, that looks like that's it for the questions. So thanks again for a super interesting talk.
Pleasure. Thanks a lot.
Have a good night.